In this video, we discuss the method of undetermined coefficients. This is a method for solving non-homogeneous differential equations. On that one pen that doesn't work again. This allows us to find y sub p, that's the particular solution to the non-homogeneous ordinary differential equation under certain conditions. So here are the two conditions. We can use this when the corresponding homogeneous equation has constant coefficients and we will use this when the right-hand side, that's after all of the y's and y's derivatives have been moved to one side and all of the functions of the independent variable only have been moved to the right-hand side. So we're going to use this when the corresponding homogeneous ODE has constant coefficients and the right-hand side is an exponential, a polynomial, a sine or cosine function, or some finite sum or product of these. Basically, the idea is that if the right-hand side is an exponential, a polynomial, or a sine and or cosine function, or a sum of those, or a product of those, then we're going to guess that y sub p, that's the form of the particular solution, has the same form as that right-hand side. And so before we get into that, let's just review a couple of facts about non-homogeneous ODEs. So remember, if we have a non-homogeneous linear ODE, and this time we want one with constant coefficients so that we can use this method. Well, actually, no, let's not restrict ourselves to this method. Not yet. So if we have a non-homogeneous linear ODE, it's going to have this form. You'll have some coefficient function times the nth derivative of y with respect to your independent variable, plus some other coefficient function times the next lower derivative of y with respect to your independent variable, and so on. And you keep going indefinitely until you get to some coefficient function times the first derivative plus a coefficient function times y. If you have all of these on one side, and then you move all the functions involving your independent variable only to the other side, remember this is a linear ordinary differential equation. It's nth order, and it's non-homogeneous if that right-hand side g of x is not equal to 0. So if g of x is always 0, like it was in all of those problems that we worked when we studied the methods for solving homogeneous ODEs or homogeneous linear ODEs with constant coefficients like this. So that's a homogeneous ordinary differential equation. If that right-hand side was something other than a 0, like sine of x, that would be a non-homogeneous linear ordinary differential equation. Now remember, when we talked about preliminary theory, we said that the general solution of a non-homogeneous linear ordinary differential equation looked like this. It has two parts. It's equal to y sub c plus y sub p, where y sub c is called the complementary function. or the complementary solution. This is the, whoops, there we go. This is the solution to the corresponding homogeneous differential equation. And I'm going to denote that by dE sub h. So we solved the corresponding homogeneous equation first. That gives us y sub c. And y sub p is a particular solution to the non-homogeneous equation. I remember when I was a differential equation student, I didn't understand that. I thought, if I have a particular solution to this equation, why do I need this solution? Why do I need the y sub c? And the reason I need the y sub c is because I'm looking for the general solution. I'm looking for the family of solutions that contains all possible solutions to the differential equation. And this turns out to be the family of solutions that includes all possible solutions to the equation. Okay, so that's what we need. We need this part and this part. Now, if this has constant coefficients, the corresponding homogeneous equation would just have a 0 over here. And then we can solve that corresponding homogeneous equation by letting y equal e to the mx. To find y sub p, we need another method. And that's what this section is about. We're going to learn how to find y sub p in the special case when the corresponding homogeneous ODE has constant coefficients and the right-hand side is an exponential, a polynomial, a sine function, a cosine function, or some finite sum or product of those. So this is the method where we guess. A lot of students are like, oh no, I don't want to have to guess. But actually, you're just making an educated guess, and it's actually not nearly as bad as you think. So let's say the right-hand side, we're denoting that by g of x. Let's say that g of x is x cubed minus 5, or I wrote x squared minus 5. X squared minus 5 will work just fine. If the right-hand side is something like this, which is a second degree polynomial, here's your educated guess. You want your educated guess to be a second degree polynomial. Since the right-hand side is a second degree polynomial, I'm going to guess that y sub p is a second degree polynomial. So I'll guess that it's ax squared plus bx plus c for some unknown constants a, b, and c. That's why this is called the method of undetermined coefficients, because we're going to say, I think y sub p looks like this because of the form of the right-hand side. And then I'm going to determine these undetermined coefficients. I'm going to figure out what a, b, and c have to be to cause this function to satisfy that non-homogeneous ordinary differential equation. So that's one right-hand side. If the right-hand side is 7 times e to the 3x, that's a constant times e to the 3x. Our educated guess would be a constant times e to the 3x. If the right-hand side is cosine of 2x, our guess would be a constant times cosine of 2x plus, get this, a constant times sine of 2x. Now, if you're wondering, why do you need the cosine and the sine? Or even, why does this method even work at all? Here's the idea. If this right-hand side has constant coefficients, or left-hand side has constant coefficients. So we've just got constants times derivatives of our unknown function. And then we're going to add all of those guys together, and we're going to get this function on the right-hand side, which looks like this. If the right-hand side is a second degree polynomial, derivatives of a second degree polynomial, they're just lower degree polynomials. If I take this function and its derivatives, and I multiply them by constants, and I add them together, for the right choices of A, B, and C, I could get this second degree polynomial back. And the same thing is true here. If this is a constant coefficient, or if these are constant coefficients on this left-hand side, these are just constants times the derivative plus, or and times the function itself. So if I'm hoping that I will take those derivatives, multiply by constants, and add them together and get 7e to the 3x on the right-hand side, it makes sense that I would guess that y sub p is a constant times e to the 3x. Because if I take derivatives of that and multiply by constants and add them together, I should expect to get something that looks like that. Now this one is a little bit less intuitive, but I think if you think about it, it makes a lot of sense. You might ask yourself, what types of functions can you multiply by constants and add together to get a cosine of 2x back? Well, derivatives of sine of 2x lead to constants times cosine of 2x. And second derivatives and fourth derivatives and sixth derivatives and all the other derivatives of cosines lead to more cosines, because derivative of cosine is negative sine, derivative of negative sine goes back to cosine again. So if I take the derivative of this twice, I'm going to get functions that look like this. If I take the derivative of this, an even number of times, I'll get functions that look like this. If I take the derivative of this an odd number of times, I'll get functions that look like that. So it makes sense that for some choice of constants a and b, if I take the derivative of this the appropriate number of times, and I substitute into the left-hand side of the differential equation, then we multiply those derivatives by constants and we add them together, we're going to get a right-hand side that could be equal to cosine of x. So here is a guide for your educated guesses. If g of x is an nth degree polynomial, your initial guess for y sub p should be an nth degree polynomial. Now, be careful. A lot of students make the mistake of thinking that since that has an x squared term and a constant term, that they just need the ax squared plus b. But you don't. If that's a second degree polynomial, you want all the possible terms there. So I want ax squared plus bx plus c. If g of x, or the right-hand side, is a constant times an exponential, and maybe this exponential is e to the kx, then I would guess that y sub p is a constant times e to the kx. If g of x is a sine or cosine of kx, then y sub p is not just one of those terms, but it's that linear combination of both of those. Y sub p is a constant times sine of kx plus a constant times cosine of kx, because derivatives of functions like these lead to functions like that. Now, if you have a sum of terms, like maybe, just for example, maybe you have g of x equals x cubed minus e to the 4x, you just take the guess that goes with this one and the guess that goes with that one, and you add them together. So my y sub p would be, well, a third degree polynomial for this. So ax cubed plus bx squared plus cx plus d. And that's a constant times an exponential. So I would guess that that is a constant times that exponential. And then what about products? What if we had 2x times e to the negative 3x? Well, that's a linear function times an exponential. So I would guess a linear function times the exponential. And you want to keep the k there, because derivatives of expressions like this lead to expressions like this. Now, I've seen some people that add an extra c over here. They'll have ax plus b times that whole quantity times c times e to the negative 3x. The c is not necessary, because c times b is just going to lead to a different constant, and c times a is just going to lead to a different constant there. So you really just need that polynomial times the exponential function, polynomial of the right degree. Now, if there happen to be sines and cosines, then your guess is going to be a little bit different. So let's say we had x times sine of 2x minus e to the negative x times, let's just see cosine of x. Well, this is a linear expression multiplied by sine of 2x. So I would expect a linear expression times sine of 2x plus a linear expression times cosine of 2x. That would be my guess for this first term. Here I've got an exponential times cosine, so I would guess a constant times that exponential times cosine of x plus a constant times that exponential times sine of x. And I'm using sine and cosine of x because this is a cosine of x here. Since this is a sine of 2x, I need a sine of 2x and a cosine of 2x over there. So it's basically you take the guess for this part and this part and you multiply them together. And you take the guess for this part and this part and you multiply them together. And if you have a sum of terms over here, you add those in your y sub p. So let me show you one example. And then I'll show you kind of where the method fails. So let's say you've got y double prime minus 4 times y prime plus 3y equals, let's say, 2 times e to the, let's say 3x minus x squared. Okay, so if I'm solving this non-homogeneous differential equation with constant coefficients, since the right-hand side is an exponential plus a polynomial, I can use the method of undetermined coefficients to solve this. The first thing that we do whenever we're solving a non-homogeneous differential equation is we solve the corresponding homogeneous equation. So let's state the corresponding homogeneous equation and then solve it by the appropriate method. So the corresponding homogeneous equation comes from setting that right-hand side equal to 0. So we're going to solve that. That's a constant coefficient equation. So we'll let y equal e to the mx, then compute y prime, then compute y double prime. And then when we substitute into the differential equation, we get y double prime minus 4 times y prime plus 3 times y equals 0. If this is a solution to this differential equation, then this equation is satisfied. And then you can factor out the e to the mx. And if this times this equals 0, this equals 0, or this equals 0, but exponentials are always positive. So we'll have m squared minus 4m plus 3 is equal to 0. And we can factor this one. That factors to m minus 3 times m minus 1. If this times this equals 0, either the first factor equals 0, so m1 equals 3, or the second factor equals 0, so m sub 2 equals 1. So that means our first linearly independent solution to the homogeneous equation is e to the m1x, so it's e to the 3x. And our second linearly independent solution to the differential equation is e to the m2x, and m2 equals 1, so that's e to the x. So we stated the homogeneous equation. We let y equal e to the mx. We computed y prime and y double prime. We substituted into the differential equation. And then after substituting into the differential equation, we simplified. And then after simplification, we solved for the characteristic equation for m1 and m2. And then once you have m1 and m2, You can use those to state the form of y1 and y2, and then you know what the complementary function is. Since it's a first or a second order differential equation, the complementary solution or complementary function has that form c1y1 plus c2y2. So we have c1 e to the 3x plus c2 e to the negative x, and that's the complementary function. Now we want to look at the non-homogeneous differential equation. So go back to that original differential equation that we started with. And now we want to write down our educated guess for the form of the solution to this differential equation. This is just a guess. This is what you're going to try. Most of the time this guess works. There are some times when it doesn't work, and I'm going to show you how you can recognize just by looking at it that it's not going to work, and then how you can adjust to come up with a y sub p that will probably work. Okay, so I look at the right-hand side and I see a constant times e to the 3x. So I'm going to guess a constant times e to the 3x. And then over here, I see a second degree polynomial. So I'm going to guess a second degree polynomial, bx squared plus cx plus d. Now, if I substitute this into the differential equation, it turns out that this is not going to work because a constant times e to the 3x is actually a part of that y sub c. Remember, e to the 3x is a solution to this differential equation. If you take the derivative twice, you get 9 e to the 3x. If you take the derivative once, you get 3 e to the 3x. So you have 9 e to the 3x minus 4 times 3 e to the 3x. So that's 9 minus 12 e to the 3x. So that's negative 3 e to the 3x plus 3 e to the 3x equals 0. So this is a solution to the homogeneous equation. And if we multiply by a constant c1, remember from preliminary theory, if this is a solution, then this times c1 is also a solution. And so since this times c1 is a solution, if I substitute in a times e to the 3x up here, or down here, all of those guys are going to cancel. This is a solution to the homogeneous equation. I'm going to get a 0. I'm not going to get a constant times e to the 3x from this. Since this is already a part of my y sub c, meaning this is a solution to the homogeneous equation, it won't give me what I want. So I know that this isn't going to work. This isn't a good guess for this part. So I'll multiply by an extra x. And it turns out that by multiplying by an extra x, this is no longer a solution to the homogeneous equation up here. This is not, we don't have a constant times x times e to the 3x in this solution. So this one's going to be okay now. That will work. And then we don't have a bx squared or cx plus d in this solution. So this part of the guess that goes with that negative x squared is fine. So we leave this part of the guess alone because we don't have any of these terms over here. But we take this part of the guess, which was a solution to the homogeneous equation, and we could tell that it was a solution to the homogeneous equation because it's one of the terms in our y sub c. We had to multiply that part of this guess by an extra x to make it work, to make it the type of function that could give us that 2 e to the 3x back. Okay, so let's find the values of a, b, c, and d that cause this function to satisfy this differential equation. In order to do that, I write down my guess, and then after I write down my guess, I'll take the first and second derivative of this function. Now this one requires a product rule. That's my first factor, and that's my second factor. So to take the derivative of that, we get, we do the derivative of the first times the second, and then we add the derivative of the second, that's 3 e to the 3x, times the first, which is a times x. It's derivative of the first times the second plus derivative of the second times the first. That's the product rule, that's for that guy. And then the derivative of bx squared is 2b times x. The derivative of c times x is just c, and the derivative of d is 0. Then we compute y double prime, Take derivative again, so you have 3a e to the 3x. And then this requires a product rule. I'll call that my first function this time and that my second function. So this is the derivative of the first times the second, undifferentiated, plus derivative of the second. Derivative of e to some power is e to that power times the derivative of the inside times the first. And then we add the derivative of this constant times x, which is just the constant. Oops, that's a b, not a d. And then the derivative of the constant c is 0. So I think I will collect like terms here. I've got 3a times the exponential plus a 3a times the exponential. So that's 6a times the exponential plus this guy, that's 9ax times the exponential. I'm factoring my exponential out. And I've got that right there. That's my y sub p double prime. And then down here, or well, up here for y sub p prime, I could factor out the exponential from these two terms, and I'd have a plus 3ax times the exponential plus 2bx plus c. Okay. So we use the right-hand side to choose the form of y sub p. Then we adjust as necessary, multiplying guesses by extra x's if necessary, in order to make sure that that term in our y sub p does not appear up here in y sub c. So that's not a solution to the corresponding homogeneous equation. So we choose that form of y sub p just by this, and then we modify it if necessary. Then we're saying, okay, y sub p is supposed to be a solution to this non-homogeneous problem. So let's take the first and second derivative, and then we're going to substitute into this equation. So we compute y sub p prime and y sub p double prime. And now we'll substitute up here. Now to help with the bookkeeping, I like to add these guys vertically. If y sub p is the solution to this non-homogeneous equation, when I evaluate this side at y sub p, I should get this for the right choices of a, b, c, and d. Let's figure out what a, b, c, and d would have to be so that this function satisfies this equation. So I will add vertically. So I'll have y sub p double prime here, minus 4 times y sub p prime, plus 3 times y sub p here. Y sub p double prime was this. And then I'm subtracting 4 times y sub p prime. So I want to distribute a -4 to everything here. And then I want to list terms vertically so that like terms are in columns. It's just going to help with the bookkeeping. So I've got -4 times this. That'll be -4a times the exponential. And then -4 times this piece is -12ax times the exponential. -4 times that 2bx is -8bx. -4 times the c is -4c. Oops, that's a constant term. That should be over here. Let's not do that. Okay, and then we want 3 times y sub p down here. So I've got 3ax times the exponential. And 3bx squared there, and 3cx there, and 3d here. And when you add all of those guys together, that is your left-hand side of that differential equation. Now see how nice this is? You can see cancellations. You've got 6a minus 4a there, that's going to be 2a. And then we've got 9ax plus 3ax is 12ax. Those reduce with this -12ax. So we end up with a 2a times the exponential. Or if you want, you could just write it as 2a e to the 3x without those big parentheses. Then here the constant term turns out to be 2b minus 4c plus 3d. The x term is negative 8b plus 3c times x, and the x squared term is 3b times x squared. Now this has to equal the right-hand side of that differential equation. So you're going to set this equal, this is the left-hand side of the differential equation evaluated at y sub p. You're going to set this equal to 2e to the 3x minus x squared. So the constant term is 0 and the x term is 0 over there. Now when you're setting these equal to each other and you're thinking about how to find the values of a, b, c, and d, this is actually very similar to what you did in calculus 2 when you learned partial fraction decomposition. We said two polynomials are equal if and only if the coefficients of x to the n are equal. So the coefficient of x squared on one side has to equal the coefficient of x squared on the other. The coefficient of x on one side has to equal the coefficient of x on the other. And that's because these powers of x are linearly independent in the sense that none of them are redundant, like we talked about with the Wronskian. The same is true here. E to the 3x is linearly independent from constants, from x terms, and from x squared terms. So the only way that this is equal to this is if the coefficient of e to the 3x on this side is equal to the coefficient of e to the 3x on that side. So we must have 2a equals 2 in order for these two sides to be equal to each other. And we must have the constant term on this side is equal to 0 in order for those to be equal. And we must have the coefficient of x on both sides equal to 0 in order for these to be equal. And then the coefficient of x squared on both sides, that's a 3b, has to equal -1. Those have to be equal as well. So from this we can get a must be 1. From this we can get b is -1/3. And -1/3 times -8 is 8/3. So you've got 8/3 plus 3c equals 0. So that means c equals -8/3. And then you're dividing by 1/3 again, or dividing by 3, multiplying by 1/3. So that's -8/9. And now that you have c and b, you can substitute them in here to find d. D is going to equal -2b plus 4c, and then you're going to divide each of those by 3. So it's -2/3 of b. So -2/3 times -1/3 is 2/9. And then you've got -8/9 times +4/3. So you'll have -32/27. And I guess we could multiply by 3/3 there. You've got 6 minus 32, which is -26/27. And that's D. Provided I did all my arithmetic right, and it's getting late, sometimes I make arithmetic mistakes. This is saying that if A equals 1 and B equals -1/3 and C equals -8/9 and D equals -26/7, then this function satisfies this differential equation. So we solved this system of equations for A, B, C, and D, and now we'll substitute those into the solution. So we have y sub p equals A, which is 1 times x times e to the 3x, plus B, which was -1/3 times x squared, plus C, let's see, what was our C? -8/9 times x, plus D, which was -26/27. So what that process is telling us is that if y sub p is equal to this, then this function satisfies that differential equation. Now we're not done solving the differential equation yet. Remember, the general solution to the differential equation is y sub c plus y sub p. So you take your y sub c, which was c1y1 plus c2y2. Oops. And then you add y sub p, which was x e to the 3x minus 1/3 x squared minus 8/9 times x minus 26/27. And this works for all real numbers. I'll probably do another example of this in another video, but that is your first example. Remember, when you guess based on the form of the right-hand side. And then if there's any part of your guess, any term in the guess that is part of y sub c, you multiply that guess that goes with the term up here. You multiply that by as many x's are necessary, so that that term here is no longer a solution to the corresponding homogeneous equation. Or alternatively, so that the term here is not a part of y sub c. Because if this term here is a part of y sub c, if it's one of those terms, then we know that's a solution to the homogeneous equation. And if we plug that into this equation here, we're not going to get 2 times e to the 3x. We're going to get 0 because it's a solution to the homogeneous equation. So I hope that makes sense, and we'll do another example in another video.